Hi everyone, my name's Alex Kingsbury. I'm with nLIGHT. Thank you and welcome to our seminar series. We're really happy to offer 6 sessions this week. We're going to kick it off really strong with 2 people from EOS. I'm very excited to tell you we're going to hear from Sebastian Becker, who is the head of Metal Solutions, and also Ankit Saharan, Dr. Ankit Saharan, I should say, who is the Director of Metals Technology. Many of you know that we signed an MOU with EOS, which is about optimizing the light engine and collaborating on the light engine. So our partnership with EOS is very strong and very deep, and they've done a lot of really interesting work, particularly on the process and the materials. And I'm very much looking forward to hearing what they've got to say about next level light engines. All right, please welcome Ankit and Sebastian. Thank you, guys.
Thank you, Alex. Thanks for having us here. I think laser powder bed fusion technology is still one of the more mature technologies on the additive side, and lasers play a key role. Without lasers, there's no laser powder bed fusion. The first word is L. So I think it's absolutely essential to understand how lasers play an important role in the technology. And I think what's coming online, especially with nLIGHT and their innovative solutions, and how they can, push the boundaries further and further. So I have my colleague here, Sebastian, here as well, who's mainly heading our product management solutions from the metal side. And I think with us and having a conversations, hopefully we can impart some of our thought process, impart some of our strategies, impart some of our knowledge that we've gathered over the years on how lasers can impact applications, impact this technology, and impact like real world applications with customers who are trying to resolve the problems through additive manufacturing.
Thanks, Ankit. Good morning from my side as well. So as you said, it's super important to talk about lasers, not only about the number of lasers, but how are we getting all the energy into the powder bed, right? And we saw in the history that we had different solutions of making this happen. So that's why we are now at a point where we see we can really bring customer value add with just using a different laser source, making some magic in there with the process development, and we are getting new functionalities into the part, right? And this is what we want to talk about. So feel free also to ask questions about materials, about processes, about our experience, because we are not on a super early stage, but we are in development and we are having solutions together with AMCM we can offer today. But feel free to ask your questions that we can also include this into this conversation within the next hour. So Ankit, maybe we can start with the somehow with the history. Where did we start? I mean, EOS is 35 years old now. Where did we start? We didn't start with the kilowatt, right?
No, you're right. And I think when we look at the history of metal additive manufacturing, I mean, going back to EOS, we started all with polymers back in the day in Germany. And in early 90s, just to give you guys a background how metal started, there was a company called Electrolux, who was doing a lot of metal additive and metal sintering back in the day in collaboration with EOS. And at one point in time, our founder, Dr. Hans Langer, decided to bring that in-house. And that's one reason why we have like a dedicated metals unit started back in the day. And that metals unit is actually in Finland, in Turku. And one question we always get is like, why of all places do you have a metal additive team in Turku? And that's actually the reason why, because it all started there. And I think many people might not know this, but like we've been doing additive, like metal additive, since early 90s. Like one of the first additive machines that came out is not the M250, it's actually the M160. It was a very small machine. I think that we only sold, maybe 4 or 5 of them ever in the world. Maybe you see them in museum at some point. But I think we hit it off with a 250 standard. And at that point, we were still dealing with CO2 lasers. DMLS as one of the most important terms, like not one of the most important, like one of the common terms that's thrown around at that point in time stood for direct metal laser sintering. Exactly what we did. We were sintering, we were not melting, because all we were doing was CO2 lasers. But once we switched to fiber lasers, like in the early 2000s with the 270, we were actually melting, but somehow we were still sticking with the term sintering. And it was not until, I think a few years ago, we decided that, well, everyone's throwing around sintering, and every few few times the customers would ask us like, well, how dense is your part since you're still sintering? Like, we're not sintering anymore, we're fully melting. And I think we replaced that word with DMLS. I suggested Schmelzen, which is German for melting.
Correct, yeah.
I was ruled out because they said it's not international enough, and now it's solidification.
Solidification, yeah. Yeah.
So
correct, yeah. It's solidification. And as you pointed out, we started with 200 watts, right? And then we learned in parallel with the material development you mentioned, located in Turku, that more power brings a better depth, so to say. We can go deeper, we can make material more dense. And then this was the born of the 400 watt lasers, I would say, right? And then we saw also competition coming up with 500 watt lasers and more laser power, because we saw we can increase layer thicknesses, right? It's also about layer thickness. We started, I don't know, with 20 microns, something like this, 30 microns. Nobody's talking about 30 microns anymore, right? We are at a stage where we are thinking about 100, 120 microns. So 80 micron is the new standard, so to say. And I would say 3 years ago, this was not the case. So in the last 3 years, we came pretty close to the 100 microns, because we still have enough power in the 400 watt lasers. And now it's with the AFX laser especially the case that we are going one step ahead, that we are going into the direction of 100 microns with more than 1 kilowatt. You announced a 2 kilowatt system. So let's see how we can bring this into the powder bed, right?
no, I mean, you're right. We're just trying to catch up to how many power lasers you can bring on at the end of the day. So it's always nice. And I want to tell the audience, like, this is not a monologue. Please, you guys have any questions, interrupt. Feel free to do that at any point in time. You're not going to interrupt our flow. Please.
So the max probably in the process side, they usually what classes this content.
Sure, take it. So at the moment we see that it's the machine gets heated up, right? It's the same we are seeing with copper applications, for instance, right? So we see that we can bring good in at the moment 1.2 kilowatts with a 4 laser machine. This is what we see. But there is adaptation in the cooling needed and so on and so forth, which works quite well. So I think with the possibilities of the productivity, and we will see also a video there and some pictures, we have to go closer to application development instead of having generic machines and generic products running each and every application, right? So we have to go a bit deeper into it, how the packing density is and so on and so forth, how the thermal stability of the system itself is and the cooling plate and so on. But at the moment, I would say we are at 1.2, 1.5 with the applications we tested. But as I said, we are not done yet. So, and the main goal is to make use of the full 2 kilowatts of a laser. Yeah.
Yeah, and just to add on to that, like, it's not always about the laser power at the end of the day, how much you can put into the system. It's now more about melt pool stability, like how far absorption we can do. And it's come to a fact and testament to what nLIGHT has done. We're kind of moving away from the Gaussian beam to different beam modes, and we're kind of unlocking interesting capabilities that we didn't think of before. So it could be that with a different beam shape, we're not only increasing throughput without increasing laser power, we keep the laser power the same way, but we're kind of actually even going towards non-weldables. We'll show in some slides that of certain materials that were not thought possible before. So I think that's the added benefit at the end of the day, is to how to better manage thermal stability, like Sebastian said, how to better manage at the end of the day, better melt pool characteristics, because what we're trying to do is not try to go deeper. Like at higher power, you go deeper into the melt, like deeper welds into the pool, and the deeper you go, the more keyholes you form. We're trying to come to a conduction welding as much as we can. So trying to stay at the surface and not have as much porosity. And we've felt that it's not the laser power, it's actually the beam shape that actually governs that kind of behavior.
And when you say conduction welding, it's the reason are the spatters, right? So we can see it in the video. So maybe we can jump on this.
Absolutely. So I'll play this.
So obviously, why are we using more power? Why are we using different beam shapes with these ring modes? The AFX laser is producing. The obvious point is productivity, as we mentioned, right? We see on the right side a process which is an 80 micron process with a Gaussian beam profile of 400 watts. And on the left side, you can see it with the ring mode 6 in that case. So it's a 250 micron ring shape of the laser beam running over the infill, so to say. And as you can really see, we are producing a lot of smoke which is pushed out of the machine pretty good, and the surface is still shiny. So this is the main thing, right? So as we are having a more productive process, we are producing more spatters, but not that deep in that case, that we can really bring the spatters good out and still having a good surface and a good dense material at the end. So this is the main aim. And with this, we can simply, at Inconel 718, it's a nickel-based alloy. In that case, we are at a productivity factor of 2. So it's double the productivity in the same machine with the same material and with the same layer thickness. In that case, it's also 80 microns. Yeah, this is the thing.
Yeah, and when we talk about higher productivity earlier on, we were talking about higher layer thicknesses. And when we go higher layer thicknesses, you're kind of generating more smoke, as is quite evident on the left-hand side. Left-hand side is definitely generating more smoke than on the right-hand side. And normally in conventional terms, the more smokier the process, the worse it is in terms of stability. But what you actually see here is that I think with the beam shaping, what we've been able to achieve, that even though the smoke is higher, you can actually see the condensate or the black spatter particles, the oversized particles. The left side is actually clean. That kind of challenges most of the standard thinking we've always had, that the smokier process is always worse. Like, this is a proof here that it's not the case. The smokier process can actually still be better than a standard process. And it's very counterintuitive if you think that way. And it's faster. Like, if you really look at the bed of the parts, like on the back side, you see actually as the laser is going about, there's a lot of spatter that's falling on the right side of the machine, right on the front side of the parts. Where we're talking on the left side, it's almost clean. And it's, mind you, it's still not so much on the gas flow because it's the same gas flow across both sectors. What difference is actually the beam shape, which actually makes a huge difference in how we do management of condensate and how much we manage about oversized particles generated. It kind of goes down the line as how to make the processes more stable, how to make them more boring. Sorry for saying that, like we say boring is sexy at EOS or boring is exciting, which is actually true, because now if we want to get into production, I think we're at an inflection point where we're saying, like we've been saying over the years, that, you know, additive is going to get into production. And all of you guys kind of know there's a lot of volatility in the AM market, considering how things are going and how the adoption has not been as aggressive as it should have been. But if we can make the technology boring, if we can make the technology more reliable, I think that's something that's going to help us drive adoption faster, not adding bells and whistles, which I don't think is always needed.
Yeah, correct. So when we are coming back to this video, how deep are we welding over there? Is it? We can just leave it like this. We can then jump to the next one. But how deep are we welding, Ankit? Normally with the Gaussian profile, we are six layers deep somehow, right? Also now with the 250 micron spot, we are also the same depth.
No. I think with standard lasers, depending on the materials, you go to 3-4 layers to like 5-6 layers, depending on what your penetration depth is, what your power is, and what the melt pool characteristics are. But with a wider beam and with a more distributed power profile across the density distribution on the spot size, we've been able to get like 1 to maybe like 1.5 layer thicknesses deep. Mm-hmm. I think we're still closer to conduction welding. We're not completely there yet, but I think that's a substantial step forward in our journey to trying to achieve that kind of a welding profile. Yeah, I would say.
Okay, thanks. The next topic is we need to educate ourselves, our customers, our market, so to say, right? Our community. So we are coming from super dense parts, and everybody, if you are asking a customer, what are your requirements? They say fully dense, 99.99% or something like this, right? But not every application needs that. So what we saw in the video before was factor 2 of productivity we can produce with the AFX laser with 250 microns. But we can also go far beyond factor of 2 by having adjusted requirements, getting into a better understanding together with the customer. What are your requirements? What is your application actually needed? Because then we can also push the boundaries up to, I don't know, factor 7 in productivity by just having 99% of density maybe, if the application allows this, right? So this is something where we need to talk about, and this is what I meant at the beginning. Developing generic processes helps to start for a customer developing their application. But at the end, we can just be successful together with customers if we are going deeper into the application, support the application development to come here on the right area of the x-axis where they need to be to earn the most money out of that.
You're absolutely right. I mean, we're not going to show density cubes only. That's not the most exciting part. We're going to talk about actual applications as well. I think that's where it actually matters. How are we able to get faster processes with acceptable surface quality? Like, that's the number one thing. Like, anyone talks about higher layer thicknesses, there's a general tendency to think like, okay, if I go higher layer thicknesses and I go faster process, I'm going to have worse surface finish. And I think from our customer base, we've always been told is like, go faster, go better, if you can. It's kind of always difficult task to manage. And but I think the team in Germany and Finland has been working quite a bit. So any highlight like how they tackle these challenges?
I mean, they try to differentiate between, like usual, between infill, contours, and so on and so forth. And this is what we see then also on the next slide, that we are having really a difference in having the new parameter of adjusting the beam shape, so to say, right? For the infill, we can use the big one. For the contours, we can still use the small one, which is 80 microns. And then we are having a really filigree contour in that case. So if you want to click to the next one. Yeah, there's a question.
I have a quick question. You guys said some of the challenges to overcome with inputting all that energy are going to be, just the thermal management process, melt pool stability, etc. At what point do you run into issues around the powder, the energy absorption of the powder? Have you run into that yet at 2 kilowatts?
That the energy doesn't absorb the...
Yeah, so the energy absorption of the powder, so it doesn't absorb, you reflect too much, you get, your processes become too dirty at some point.
Yeah, so we saw this really early, also without the AFX laser, in copper applications. Typically we see this behavior, something we are tackling, but also here, if we are bringing into Inconel 718 and the flow is not stable and fast enough, we also see a kind of flipping in the process, so to say, that the melt pool is just falling down, so to say, and we are not really melting in this case. Then this is what we see. Then we are not bringing any more the power into the melt pool, but then it's just absorbed by the region around, so to say. It's really about process stability over there, and it's another new parameter, a new variable we have to take care of, that it really works. But if it works and it's stable and we are bringing all the spatters out and we can keep the keyhole deep enough, so to say, not to be too deep, but having pretty close to conduction welding, then it works quite well.
And it also depends on, at the end of the day, when you look at the melt pool closely, and you looked at high-speed videos from different national labs coming out, you see like these particles getting ejected. And they're not really smoke. They are the oversized particles that fall on top of the bed on the front side, or they get caught in the filters and actually are what's kind of making your filters a little bit dirty. Or these are the kind of particles that typically land on your sieving losses when you're actually sieving your material. And what we're noticing with some of these processes is that the melt pool is absorbing these large particles back into the melt pool, thereby actually increasing the melt efficiency. If I call it that, it's not an actual word. Please don't pin me on that. But the melt efficiency on these kind of profiles is a bit higher than what we've been able to achieve with the Gaussian size.
Okay. What I wanted to say is, because you raised the question how we solved it. It's about, we have infill areas, we have lattice areas, we have contours, right? And we are adjusting the beam size, so to say, depending on on what we are doing in this case. Also the downskin, we are just slowing down, or we are making it smaller, the beam shape in that case, that we are getting a more filigree surface in that case. And this helps that we can adjust in the process, in the layer itself, between lattice, contours, infill, and also downskins over there, and this is what helps.
Absolutely. So, talking about the low cracking beam, I think, Sebastian, this was one of the parts that was done in Germany. Like, can you talk a little bit to this part?
Yeah, so we printed multiple parts, also different materials we printed there, and the density is one important point we want to keep, right? The faster we get, the normal thinking is in additive manufacturing that we are including spatters somehow, that we are having big holes in there, big pores, especially in the surface area, subsurface porosity and things like that. And there we really see that we are really dense. And this is what we are experiencing. Not only in the infill on the Lincoln S718, we also did other materials already, like aluminum, LC10MG, but also MAR247. We tested already, and there we really see that we are having a super low porosity. We're at 99.99% over there, and also the pore size itself. If we are having pores like over here, we want to go below 40 microns, right? This is the target we are having, pores below 40 microns, getting from our customers these kind of requirements, and there are we with this new, even by having such a high productivity, and this is the magic behind.
No, absolutely right. Okay, so I'll let you talk about this. I think this is one of the bigger developments coming out from EOS, but please tell us more about this.
I mean, CM247 is something which is important, or we are talking about, some people say it's the holy grail in turbomachinery, right? So, I mean, for us, it's super important that we are finding applications that it becomes the holy grail, because just talking about it doesn't make it the holy grail. So we have to show that we can use this application, that we can make this application happen on our machines with the AFX laser. And what we see over here is we printed these small parts. You can also see at the EOS booth with CM247 without cracks. So there are no cracks in there. So we can just run it on our today's platforms with the AFX laser provided by AMCM in that case. So AMCM is providing the hardware, EOS machines together with the AFX laser. And there we really made it happen that we are not having any cracks in the CM247, which is pretty good. So it's not released at this point in time. We are working on it because it's super important not to have a generic process product, but an application product. So if there is any customer interested in, we will talk about this with you, because it's important that we are getting into a common understanding there.
No, absolutely. I think if there's one material that always, if you draw a Venn diagram and say like material which is more high value components, more expensive material, something that we're going after, 247 like checks all the boxes in terms of like value for parts, and we're talking like single crystals at the end of the day. So I think that's very important to understand, is like the ability some of these new processes have given us is not only doing non-weldables, but the ability to grow single crystals. We're still directional dependent though, but again, still being ability to do single crystal is something that like a few years ago, even 2 years ago, was like you can't think about it. Like that's something, it's profound. And talking about one thing that, like I said, this is something that we unveiled as part of our innovations platform, but this is not where we stop. I think we've got a whole slew of materials roadmap on the anvil for us, trying to address and see like what this laser and the processability can do to increase the process speed. So we're talking about titaniums, we're talking about GRK42, we are talking about the new NASA alloy, which is a GRX810, the highest 3D printed alloy that can sustain the highest ever temperatures. We're talking about some of the other 738. We're talking about many more materials that's going to help unlock applications. I'm a materials person. I'm a firm believer that without materials, there's no additive, there's no applications. So the only way to unlock standard materials is to unlock new materials, and second, drive the cost per part of standard materials to somehow commodity pricing. Otherwise, like we would always be behind the 8 ball when competing with cost per part, when we're talking about value added. And keep in mind, I mean, talking about the added cost of these lasers versus the cost benefit. Like how would you address that?
Hey, Ankit, sorry, I've got a
Yes, a
question. Can I
question, yeah.
jump in?
Please.
Because you said materials, and I want to dive deeper into that. What is it about standard processing with current day printers that means that you're getting crack density that's unacceptable? And how does beam shaping change that? Talk about the metallurgy, please.
So the main portion, I mean, I'm just trying to see like what I can really talk about, because I'm always bound by like what I can say and cannot say. But what we've noticed is that the better we control the cooling behavior, like coming in afterwards, after the part's been melted, that's always crucial when it comes to non-weldable, because that's where they don't crack like when you're melting them. They start cracking behavior starts after the laser is passed over. So all I can say at that point is that the laser and the software control that allowed us to basically control this to a very precise degree for us to eliminate any cracking. And if we're talking about CM247, you would see go around the booths. I mean, there are a lot of people today who are printing 247 to a certain degree. But the main challenge where it comes about is heat treatment as well. So the cracks actually, when you get the part out of the machine, there are no cracks. When you start heat treatment,
Then
they open up. So that's always critical. And I think that's where it's a combination of the thing. Like laser is not the only solution. We're talking about the whole solution and trying to tag it up, trying to get a better laser and better process. At the same time, tackle the heat treatment side of it so as to ensure that we get a fully dense parts. That helps.
You asked the question, how are we tackling the additional
Value, cost, benefit of.
Yeah, right. So
Everyone's going to ask that.
what surprise. I mean, it's quite clear that customers are changing things, running processes, validated processes, qualified processes, once the value add is big enough, right? So we cannot come with, or we cannot tell them, okay, we are getting 20% faster, 15% faster, or something like this. So it has to be double the productivity, 3 times the productivity. And with this, cost per part goes down, right? With this, you can produce more parts, you are getting into scaling effects of buying your material and so on and so forth. So this is the big value add, that you can increase the production, or you can produce more parts per year on one system. So at the end, with this, of course, systems are getting more expensive in that case. So the capex part of and the depreciation part of your cost per part calculation is getting slightly bigger due to the fact that you are having more power in your machine, right? It's like an expensive car. A fast car is more expensive than a slow car. So this is the thing. But you are getting faster to your target, so to say, in that case. So this is what we are doing. So really talking about the productivity increase, talking about less spatters, a more clean process, and all the advantages like the full density we are getting out of this is the full value add we are bringing in this package.
No, and I would absolutely say trust us and buy the machine. Of course, we're kind of understand you need to prove first before you actually go with this one, and we've got platforms in Germany, we have platforms in Finland, we have platforms in North America as well, where we invite customers to come develop applications with us. You don't have to invest into the technology until you see the proof. Like, we're ready to present, the proof is in the pudding at the end of the day, and we're ready to prepare the pudding for you guys before you actually jump in. This is something that we want to make sure that when customers are investing into such a technology, they're kind of investing it with the most amount of risk minimized at the end of the day. Like that's from where we're kind of coming in. You don't want a fancy machine where you can't do anything with it. At the end of the day, it's the most expensive paperweight that you ever bought. We're trying to come into point, like, come with our application engineers, come talk to us. We'll work together on the applications, prove this out, that it actually works, and what we're trying to say is true. Maybe it's not true, but like, let's find out together, and then make a decision yourself. The data would speak for itself. We don't need to do that.
Yeah, we can really proudly say that it works. It works. We can see, we did a couple of tests on different sites. As Ankit mentioned, we really say it works, and now we have to find out how we can help you with your applications.
Absolutely.
Any questions from your side?
I'm curious, for the 247 to print that, do you have to print it off a 247 build plate, or?
I think we just used a steel plate, right? Yeah, it's a steel plate.
It's just steel.
Yeah.
Okay.
That's one thing always asked is like, to print copper, do you need a copper plate? I mean, you can, but like...
but not necessary.
Not necessarily. I mean, unless you want to dispose of copper plates every 2 days, because otherwise it's going to rust as quickly as it can. Mm-hmm. Same thing went to us with in-canal. Can you want to do in-canal plates? We always find that question. From our side, we're trying to, when we put out a solution, at the end of the day, we try to make it as achievable or like as tangible for our customers. We don't want to put special plates where sometimes the cost of the plate would be more than the part you're printing on top of it. So we're kind of always cognizant of the fact that it needs to make commercial sense for our customers. Other than that, it's not viable.
So maybe I say a couple of words on our product strategy, so to say. So what are we doing? We have AMCM and EOS in one group, in the EOS group, and we are offering at this point in time customized products by AMCM with the AFX laser at this point in time with 1.5 or 2 kilowatt lasers. This is how we are providing the hardware. Process development comes from the EOS group and AMCM together. Then depending on the materials, we have different sites, we are developing different materials, so then it depends actually which material, which application, and who's then going to be involved. Is it the Finnish team or the German team or the North American team in that case? But hardware is going to provide at this point in time via AMCM.
And from an application development side, coming from the Additive Minds team on the global side, we are providing support and applications development for customers across the globe. So whether you have an application or a customer in Asia Pacific, EMEA, or North America, we're more than happy to support any application locally with the local teams available to talk the language that you guys do, speak the same challenges that you guys are facing, so that it actually provides the most benefit of the conversation.
Yeah.
One question, if I may ask, Sebastian, are we providing these lasers today?
I mean, as said, we are providing it via AMCM. In that case, we are at EOS. We are working on integrating it also into our platforms. So at the moment, we have via AMCM solutions in the M290 platform, which is the smallest one, I would say, on the M304 with 4 times the AFX laser, and then also in the M450 via AMCM. This is what we are providing. Then let's see how in which system we are integrating it at EOS. This depends a bit on the numbers, so to say, right, on the sales numbers. But that's why we have our speedboat AMCM taking care of this in this early stage.
Perfect. So bottom line is we can access the lasers. Customers have access to it, either whether they want to use it as a playground to do application development with EOS, or they want to buy platforms together with EOS, retrofitted with these lasers. It can be done. Can customers upgrade their CapEx investments that they already have with these lasers?
This is currently under investigation, so I cannot commit to this at this point in time. So we're looking into this on the M4 platform at the moment and also on the M3 platform. But this is, something which is not clear at this point in time in R&D.
Yeah.
Ankit, I've got another question for you. I know you're basically an internal customer of EOS, right? Working in the North American group, but working very, very closely with customers, and in that sense being sort of like a customer advocate internally within EOS. What are some of the things that you're most excited to be starting to work on? Because I know you've just got your new M290 with nLIGHT-AFX. So what are you looking forward to working on most?
We're very excited to actually take the processes that the German and Finnish teams have developed to North American, because certain North American customers, certain applications cannot be exported outside the border. So I think there's a lot of potential that people are just waiting to try on the machines. We're just trying to manage how we're going to address whom first. I think that's my biggest challenge right now. But what I'm really excited about is for the team to basically explore, because for now we've been limited to power, speed, hatch distance, and this kind of adds another variable to that. And I'm really excited with my team to explore what that extra dimension is going to add to existing processes. And I always tell my team, with these kind of things, you can throw the equation, energy density equation, which is power divided by hatch distance, layers, thickness, and scan speed. You can throw that out of the window. That's no longer valid. But I think that's what we're most excited about, is that what else can we do? How can we bring more commodity materials at a more cost-effective price? Like with additive, we've always been, on one side, always been very excited to bring new materials which are suited for this process, because the existing materials are not workable in the process. But with CM247, we've shown that the commodity materials or existing standard materials can be done. So I'm more excited about how many more other standard materials can we bring to the market at a cost competitive price that our customers can find value in.
Does anyone else have any more questions? No, that's right.
Thank you so much.
Okay, all right.
Thank you.
Thank you so much for that talk. It was really good, and we really look forward to seeing what happens over the next year with EOS, because I think that there's been so much progress made in such a short space of time. And yeah, we're really excited to see what happens next. So thank you very much. Please hang around for a photo and maybe a speaker gift or two.
Thanks for the invitation.
Of course, and thanks very much everyone for joining us.
Yeah.